And in the discussions that we've had with various folks, we've run into, I would say, arguments against applying DOE to cyber testing that are analogous to the kind of arguments that I ran into when I was the director and actually had the authority to mandate the application of DOE in developing temps and tests. And it won't surprise you if I observe that I don't find most of these arguments particularly cogent. Not to say that I haven't learned a lot by engaging in these kinds of arguments, and the content of this briefing actually reflects some of the things that I've learned from discussing these things with folks. Now, I start out here on this chart with an observation about the DoD Cybersecurity T&E Guidebook. And of course, I'm not sure it's called a guidebook anymore, and I'm not sure what state it's in. What these things are called and what their content is going to be seems to be continually changing, and frankly, I can't keep up with all of it. But a previous version of the guidebook that existed had this quote in it. And my view, obviously, is that DOE can help promote data-driven, mission impact-based analysis and assessment methods for cybersecurity test and evaluation. And I hope in this discussion, in this presentation, that I'll be able to show you how that might work. And I'm not going to read through the benefits that DOE offers when designing any kind of tests. I think you should all be familiar with them. But I hope to show that DOE offers those kinds of benefits, in particular for cyber testing. Now, I stole this chart from some material that the Operational Evaluation Division here at IDA developed, so it must be really good. And it shows the steps involved in planning any kind of experiment or any kind of test and evaluation program. And the designs of any kind of test start out with the application of subject matter expertise. The designers of the systems get together with the people who will use the system. Sometimes it's just the designers initially getting together among themselves and thinking about what the problems with the system might be and what data they want to collect on the specifics of individual box designs and that sort of thing. But eventually, the group of people who are interested in figuring out how the system works will expand to the users. But it always begins with the application of DOE always begins with the application of subject matter expertise. To design the tests, to first of all figure out what the factors are, to postulate what the response variables might be, and so forth. And then, the people with expertise in DOE and in particular statistical expertise get involved in helping those folks actually develop a test design. And then the tests are conducted, and the people with statistical expertise and expertise in DOE help in analyzing the data. But in fact, and it was certainly my experience, for example, in the Joint Strike Fighter program, among others, that it was best to involve the analytical experts and the DOE experts from the very beginning and all along. But the green boxes show where those kinds of folks can have quite a bit of impact, but involve them all along, including from the beginning. So what I'm going to show here today, or discuss today, are, two potential ways of applying DOE. One is in determining the scope of the test and starting to figure out what the specific vulnerabilities are that you might be interested in exploring in more detail, and then applying DOE after you've used it to determine the scope of the test, applying DOE to actually develop more detailed test designs once specific vulnerabilities and potential attacks of interest have been determined. So I'll talk first about a way that DOE might be applied to perform a systematic cyber assessment. For example, it might be used to help guide a cyber risk assessment, or whatever they're currently going to be called. and I'm going to use a hypothetical processing system. It's hypothetical, but it's based on a real-world example that I'm not going to discuss because I don't want to have to worry about CUI and everything else. So my hypothetical system is displayed here on the right of the chart. It has 15 subsystems that perform various functions, and it has 2 operations consoles. And so I am going to talk about a way that DOE could be applied to help guide a cyber risk assessment of the vulnerabilities associated with those 15 subsystems and 2 operation consoles. Now, I am assuming, and I haven't yet demonstrated, that you can build a statistical model with factors and parameters and responses for these kinds of cyber assessments. Otherwise, for example, developing a de-optimal design doesn't make much sense, because you have to form an information matrix and take its determinant, maximize it, for example, if it's a de-optimal design, and that all works only if there is some statistical model that exists with parameters. And so I'm assuming that that's the case. And I'll suggest in this particular case, in a cyber risk assessment, that the response variables could be, the responses you're interested in could be what the subject matter experts sitting around the table might rate the severity of the potential vulnerabilities that they begin to identify, how they might rate them on a Likert scale, where they might rate them high, medium, low, non-existent. So I can at least imagine that there are response variables, and the factors might well be the individual subsystems. So I might identify a potential vulnerability with subsystem 1 that many of the subject matter experts rated 5 on a Likert scale. So I can at least imagine that the statistical model that underpins all of this can exist. So I am assuming that. I haven't demonstrated it yet in practical applications, but I'm assuming it here. So the way I'm imagining that this assessment would work, guided by DOE, is that you would try to narrow the number of potential vulnerabilities, first by looking at attacks on individual subsystems. And I'm going to assume that those attacks originate in the operations consoles, because I'm assuming that that's really the only way into this system. And again, this is based on a real-world system that actually it uses encrypted communications, so you'd probably have to be an insider and sitting at one of the operations consoles in order to really get into the system and do anything to it. But I'm going to first look at attacks from one of those operations consoles targeting a single specific subsystem. And then I'll discuss how you might look at attacks spanning multiple subsystems. Because that was something, for example, that Mark Carrera brought up when we discussed these ideas with him. And he's certainly right. You can imagine attacks that would span many different subsystems. So I don't want to read through this chart, but attacks beginning in one of the operations consoles, the remaining subsystems are targets. I'm imagining, in this particular case, nearsider and insider attack postures, but not any outsiders, because there's really just no imaginable way in this particular case for an outsider to get in. And I'm imagining looking at native and foreign tools, and there are 120 total combinations. And again, I'm assuming that there's a statistical model that can be built, an information matrix that can be constructed, and so forth. And I'll consider 68%, which I would say is minimal, and 80% power to correctly assess, identify vulnerabilities, and 80% confidence. And again, so what I'm imagining here is the SMEs are sitting around a table, probably together with some red team kinds of people who have expertise in attacking this kind of system, in exploiting it. And they are looking at each subsystem and what it does, and the protocols that are used by people sitting at the operations console to communicate with each particular subsystem. And they are identifying potential vulnerabilities, potential ways of attacking, either with native or foreign tools, and what might happen if those kinds of attacks were launched. So a run, in this case, is an assessment by the subject matter expert group of what might happen if somebody sitting at one of the operations consoles was able to do something and get into one of the subsystems. And so you might not have the time to just sort through every one of the 120 total combinations here. And so you apply DOE, and you end up with this kind of matrix of considerations of vulnerabilities, not looking at every subsystem, but assessing 45 potential vulnerabilities, and that would give you 68% power and 80% confidence, and if you assess 65, then you get up to 80% power. Again, this depends on constructing whether you can construct a statistical model. Now, as I mentioned at the outset, you can certainly imagine attacks that get into one subsystem but then hop among subsystems. And there's work that's been done, and I'm making a leap here, I'll admit. There's a lot of work that's been done by NIST on how many different combinations of input data or configurations of a system are involved in vulnerabilities and faults. And the people who have done this work at NIST stress that it's not just input parameters that they're talking about, different combinations of input parameters, but it's also different system configurations. So I'm going to assume that it's fair to consider the number of subsystems involved in a particular attack thread as a configuration. And if you do that, and again, that's a leap, it gives you some hope that if you look at attacks spanning 2 or 3 subsystems, you may have picked up the majority of the vulnerabilities, the potential vulnerabilities in the system, as demonstrated on this chart, which I took from NIST. So let's look at attacks spanning 2 subsystems. And in that particular case, the number of combinations you're interested in has just gotten larger. You've gotten up to 224. But if you apply DOE, you can assess 50 potential vulnerabilities covering 224 combinations with 68% power, and you can get up to 80% power with 65 assessments by assessing 65 of those different combinations, as displayed here. So let's go up to 3, because, again, back to this chart where I'm making a bit of a leap. I want to get a little bit further up on that curve, but I don't want to go all the way out, because obviously you get to the point of diminishing returns if these kinds of data are applicable to what I'm trying to do here. So let's look at attacks spanning 3 subsystems. That's 1,248 total combinations. Again, if you apply DOE, assuming there's a statistical model you can build, you can see what happens. Now, I've made a couple of leaps here. I haven't actually demonstrated that this works, and one way you could imagine that is to basically do what's been done in the past with red teams poking around on the system, on this kind of system, and keep track of vulnerabilities they find, probably over a considerable period of time, and compare that with the results of this kind of an assessment. At least I can imagine doing that. Hasn't been done yet. I'm not sure it will ever be done. But obviously, in my view, this way of thinking about cyber tests could be very useful. What we keep finding out in the attacks that occur is that although we learn a lot from individual red team events, and penetration tests, there are always many vulnerabilities that haven't been found. And there are always many, many potential vulnerabilities, so it's not a surprise that any given red team event or any given assessment doesn't find them all. I see this way of applying DOE as helping to provide a more systematic way of assessing all of those potential vulnerabilities without having to think about every one, which nobody's ever going to be able to do anyway. So, I will state somewhat boldly here on this chart that I think I've demonstrated how you might apply DOE to help determine the scope of a test when there are many potential vulnerabilities that you could be concerned about. And now I'll talk a little bit about how the work involved in marching through these other little thin rectangles might go. And in particular, I'll talk a little bit more about designing more specific tests by applying DOE, cyber tests by applying DOE. So I'm thinking about here either a cooperative test or an adversarial test. And again, I'm not sure what the current lingo is here. And I guess, frankly, I'm not really all that interested but in what the current semantics are, because I don't consider it all that significant, even though a lot of other people do. But I think most people here will know what cooperative tests were or used to be and what adversarial tests used to be. At least those were the terms that were used when I was in the building. Potential response variables, and some of these might actually be factors, but these are the ones that came to our mind, and in fact there are some OED publications, and again, if they're OED publications, they must be good, that also include these kinds of potential response variables or potential kinds of pieces of information you would want to collect during tests. And some of the people that are out there in the services thinking about doing cyber tests are also using these kinds of response variables, which may mean that they're not particularly profound. They sort of come immediately to mind. Having said that, I certainly didn't see when I was in the building and signing out cyber tests, test results, systematic collection of these kinds of response data. But it seems to me that if we are all serious about doing cyber testing, we ought to treat it like all the other testing, and we ought to be able to identify response variables and data that we want to collect, rather than just, oh, we got in and here's what happened. Again, you can learn a lot from that, but you're also potentially missing quite a bit. And I'm not going to read through every potential factor here. These are the ones that came to mind. We don't, again, regard these as horribly profound, and others have talked about these kinds of factors. But these are the ones that we're going to consider in a little bit more detail in trying to show how DOE could be applied to develop a more specific test design. We're imagining here a sequential approach, which I've hardly ever seen used. Usually it's one test and you're done, which of course is not the way you should do it. But we're imagining here that you would screen and then refine. Again, I've hardly ever seen that done, but it should be. And we discuss in some of these bullets how the cyber and systems subject matter experts need to be involved right from the start and throughout. I do make an observation here, and it was my experience that when the red teams, actually it was just when the red teams would actually go out to do a penetration, to do an adversarial assessment, or to do attacks on a system, they would run into problems actually being able to do everything that they thought they might really need to do or should do. Because the operators were understandably concerned about what might happen on their system, because usually the way these tests are done, they're done on live systems. The operators were concerned about what might happen if the red teams actually caused something bad to happen. And so there were rules of engagement that oftentimes got negotiated at the last minute that were very constraining. Well, I mean, this kind of an approach, applying DOE, you can show what the effects would be on power and confidence on your risk of drawing incorrect conclusions based on the test results if the rules of engagement are too constraining. And that's true of any test, but it's also would be true of a cyber test, designed, developed using DOE. And some people have expressed concern about learning effects, but there are ways to control for learning effects that I'm sure you're all familiar with, and that can be used in any kind of test event, and in particular, if you're designing cyber tests using DOE. I've talked about the statistical model. We really use this chart to try and explain to people who aren't familiar with statistical models what the concept is. And I am imagining that this kind of statistical model could be developed. And I've talked about what the factors might be and what the response variables might be. So, again, looking at the little blue and green elongated rectangles, let's look at developing a test design for a hypothetical command and control system. And again, these are all hypothetical because I didn't want to have to worry about CUI and all that sort of stuff. Here's a hypothetical command and control system that's web-based. There are a number of external systems that connect to it using a couple of different protocols. There are user terminals that connect, as shown in the chart, using 3 different protocols. There are maintenance protocols. Anyway, you can read the chart. There are various protocols and various systems, either external or directly connected, that interact with an application server, a web server, and a database. And so I'm thinking about the protocols and entry points. So here are the factors, protocols and entry points, starting posture. In this particular case, since the thing is web-based, and because of the kinds of protocols that are used, I'm also imagining outsiders could penetrate the system. Looking again at forward and native tools. In this particular case, we're considering network load of low and high. That can make a difference because it can make a difference in the logging that occurs and how prolific all the logged events are and how well or not the operators are actually paying attention to what's happening in the system. In this particular case, we're also considering the level of defender participation, whether it's just the local users or the users and local defenders or the users, local defenders, and a more remote security monitoring system. And we generate a 40-run design providing, somewhat sparse coverage of a 288-factor space. So again, this is a more specific design. I'm imagining here that there are particular kinds of native and foreign tools that are being used that have been identified as potentially working against the particular protocols using the entry points, the particular entry points. This has all been identified, perhaps in a cyber risk assessment. And so this would be a way of designing a more specific test, either a penetration test or an adversarial test, an attack, a series of attacks. And a 40-run design covers fairly well, but nonetheless sparsely, this 288-factor space. So again, I see the potential advantage here being you've got a systematic way of understanding what you've covered and what you haven't in terms of potential vulnerabilities. This is a much different way of thinking about doing cyber testing than I was certainly aware of when I was in the building. The cyber testing I was familiar with went something like, there were cooperative tests that were done that identified some potential vulnerabilities. That information was passed to a red team. By the way, there was debate about whether that should occur, but everybody, including me, decided that the red teams weren't going to have time to do a lot of reconnaissance, so they should be able to take full advantage of whatever penetration testing or cooperative testing had been done previously. So the red teams come in, they're familiar with certain kinds of attacks. Maybe they have familiarity with the system, maybe they don't. They basically experiment, find a way in or two, and the test is over. Now, that doesn't mean that the program and the department haven't learned a lot from those kinds of tests, but you really don't have a very good idea of how much of the space and potential vulnerabilities you've covered using that kind of process, which was the one that I saw being used time and again, and I'd be surprised if it has changed much. I'm suggesting here that there's a more systematic way of designing these tests that could give you a better idea of the number of potential vulnerabilities or the space of potential vulnerabilities, how well you've covered it. But this would be a much different way of designing cyber tests and executing cyber tests than has been done in my experience. And this gives some of the power estimates that were done for this, that we generated for this design. There were no major confounding between factors. So that's an example of how you might apply DOE to generate more specific test designs once you've done something like a cyber risk assessment, which identified some specific attacks and specific vulnerabilities that you would be interested in exploring in greater detail. So the examples of analysis that I have here I think ought to be familiar to anyone who has been applying DOE to testing. You get data. Here's a notional distribution of data for a continuous response, like, for example, time to penetrate. You can perform an exploratory analysis looking at the level of the response variables, the levels of the response variables. You can then the analysis can then indicate to you whether there are significant differences, for example, between native and foreign tools. And I know OED has performed this kind of analysis, not in the context of a test design, but in the context of looking at the results of tests after they've been done. And there might be differences between the starting posture of the attacker that you could discern. Similarly for protocol and entry point. So what I'm suggesting here is you could apply DOE to cyber testing the same way it's being that has been applied to operational testing and to developmental testing, and reap the same benefits, the same kinds of benefits. It hasn't been done yet. I hope that it is done. I hope that these kinds of discussions help to make that happen, because I see some real benefits in applying DOE to cyber testing and helping the department and particular programs understand better how vulnerable they may well be. And that's it.
Jason Sheldon from RDA. A question about actually implementing this in a test. What would one run or one shot look like? When I think of a cyber assessment, I don't think, like, I understand the starting posture is a factor and the tools used is a factor, but and you measure maybe time to defend. But how is that, like, how can you go run by run through executing those in a test?
Well, I tried to answer that question at the outset, obviously unsuccessfully, because it's been asked before, and I understand why. It's, it's a very reasonable question to ask. So, for example, in the context of the assessment that I discussed initially, a run would be the subject matter experts sitting down and thinking about, all right, if I stop at operations console 1, so I'm talking about the processing system, the hypothetical processing system that I used in the first example. So a run would be the subject matter experts sitting down and discussing among themselves, all right, if we start at operations console 1, and what are the ways to get to subsystem 1? And if we get to subsystem 1, what effects might we have? And then, rating the severity of those effects. This would all be judgmental at this point. For example, on some kind of a Likert scale. That would be one way to do it. All right? And, that would be a run. And then, having identified, by doing that, the list of potentially highest impact subsystems, if you just get to them first. All right, well, if I got to, maybe it's subsystems 1, 2, 4, 5, and 6. I don't know. All right, if I get to those, in the next step of this process, the assessment process, if I get to those, then let me consider jumping to any of the others, what might happen? How might I get there, and what would the severity of the effects be? So in the context of the assessment, a run is the subject matter experts sitting down and thinking about what might happen, and then rating the potential severity of what might happen using something like a Likert scale. And I'm using a Likert scale because then that's a response that I could collect, right? Now, in the context of a more specific, of the more specific test design, a run would be, all right, I've identified a potential attack means using, let's say, a native tool that could be used with, let's say, protocol 1 in a user terminal that might enable me to penetrate to the application web server. And what I want to do is, for example, measure how long it takes me to get in, which isn't really telling me directly about how severe the effects might be. Or what I might do is, again, have subject matter experts, after the test has occurred, rate the severity of the effects that actually were generated or could have been generated because there are usually constraints on what's actually allowed to happen. So a run in that case would be, let's say I've done a cyber risk assessment which identified a particular attack that might work using a particular protocol from a user terminal to the web server, and then I rate the effects. Once I got into the web server, I rate on some sort of Likert-like scale the severity of the effects so that I was able to generate, or at least that I could argue I could have generated if I was allowed to. So I hope that answers your question. That's the best I can do.